They plan was to knock me out the top of the game, but I overstand they truth is all lame. I hold cannons that shoot balls of flame, right in they fat mouth, then I carve my name. Nah.
Second case with our distinct complex eigenvalues. We're going to get two eigenvalues, so we'll just say eval, that are complex conjugates. And a complex conjugate is just something that looks like this. If you have a plus bi, the symbol for complex conjugate is just a bar over the top. Complex conjugate of that is a minus bi. So that's just a complex conjugate. So we'll say our eigenvalue is a plus bi. We'll use alpha and beta instead. So alpha plus beta I, and the other eigenvalue will be alpha minus beta I. So and these will have the form t plus I squared of 4d over, or minus t squared over 2. This will be t minus I 4d minus t squared square rooted over 2. So anyway, when we have these two complex conjugate eigenvalues, we actually only need to consider one of them, and we'll see why. Well, this will lead to a complex eigenvector W, which satisfies a minus lambda I times W equals 0. And this W will have the form, since it's complex, it'll have a real part and an imaginary part. So the real part's V1, imaginary part is V2. And we use this to find a complex solution to the equation z of t. That'll be e to the lambda t times w. But if we decompose this into real and imaginary parts by plugging in alpha plus beta I in for lambda and v1 plus iv2 for w, simplifying this, we'll get e to the alpha times e to the bti times v1 plus iv2. Using Euler's formula, we can convert this into cosine beta t plus I sine beta t. And we can just distribute this. So we get cosine beta t v1 plus I cosine beta t v2 plus I sine beta t v1 plus I squared sine beta t v2. So I squared is just -1. So this is going to be negative sine beta t v2. What we can do is we can group the real parts together. So this is going to be e to the alpha times cosine beta t this should be v1 plus this negative sine beta t v2. Then we have an imaginary part, I, so we're going to factor out I. So I times e to the alpha times cosine, actually we'll start with sine. This is sine beta t v1 plus this cosine beta t v2. So it turns out that well, we don't want imaginary numbers in our solutions, we just want a real solution. And it actually turns out that this real part by itself is a solution to the equation. and this imaginary part is also a solution to the equation. So we can make our y1 equal the real part of z of t, and our y2 can equal the imaginary part of z of t. So that means that y1 will equal e to the alpha times cosine beta t b1 minus sine beta t b2, and y2 will equal e to the alpha times sine beta t v1 plus cosine beta t v2. And our total solution then, y of t is going to equal c1 e to the alpha times cosine beta t v1 minus sine beta t v2 plus c2 e to the alpha sine beta t v1 plus cosine beta t v2. So it's not really necessary to memorize this. It's better just to memorize the process, and it'll be easier once we see an example. So let's do our third case. Third case is where we had one real eigenvalue, and that eigenvalue is going to be t over 2, and it has an algebraic multiplicity. I'll just call it am2. So like we said before, there's two cases. Our first case is where the geometric multiplicity of the eigenvalue equals 2. That means the eigenspace, that's just the space spanned by the two eigenvectors, is just going to be the entirety of the plane R2. So you can always just make v1 equal 1, 0 and v2 equal 0, 1 because those two vectors form a basis of R2. So y1 will just be e to the lambda t v1, and y2 will equal e to the lambda t v2. So our total solution is c1 e to the lambda t v1 plus c2 e to the lambda t v2. Let's look at the second case. Our second case is where geometric multiplicity is equal to 1. So we only get one eigenvector, v1. That's going to, that's just going to satisfy a minus lambda I v1 equals 0. But we need another eigenvector, and well, first let's see, this will correspond to a solution e to the lambda t v1. And we need a second solution because this is a 2 by 2 system. So the solution is actually going to have the form y2 equals e to the lambda t v2 plus t v1. So we know what v1 is, we know what lambda is, so we just need to find out what v2 is. v2 is just going to be a vector that satisfies a minus lambda I times v2 equals v1. So if we solve this equation, we can find v2. So once you get v2, then we'll have y1 and y2. Our total solution then is going to equal c1 e to the lambda t v1 plus c2 e to the lambda t v2 plus t v1. And those are our three cases.
Oh, 56, nigga, shut the fuck up. Fuck that nigga, run that back. Money.
Run that back, man.
What?
I gotta get hot, man. You gotta
run it back. Run it back? Alright, run it back.